Welcome to the 2023 Spring Summit for VoltServer AgMesh. I'd like to start this presentation by introducing our technical directors, Camilo Giraldo and Stanley Milnick from VoltServer, along with our team members, Andre Costa, Edgar Ponce, Zach Chauffet, and Rowan Woods. Our sponsoring company, VoltServer, is located in East Grand, Rhode Island. They're the creators of Digital Electricity, which is a fault-managed power distribution platform, which means that it's safe to touch electricity.
One of the main motivations for this project is being able to contribute to the development of new technologies that will be used for smart indoor agriculture. This project is allowing us to collaborate with VoltServer to develop a prototype that will allow for future development of these devices. The understanding of different plant types, the amount of that light they need, different requirements that allow them to grow efficiently are all being taken into account when developing this prototype. Our project would also allow for maximized results, whether that means plant growth or efficient energy consumption. Our prototype will allow for minimized maintenance as it is being developed to withstand different adversities that it may face inside a greenhouse. Digital electricity also plays a huge factor in minimizing maintenance costs, as systems such as the DE transmitter that we're working with are very effective in what they do. The fact that our prototype will be fully autonomous and it will only require a single input from the user in our GUI also allows for reduction of labor as well. Finally, the dimming of light when the maximum light levels are now required will not only save money, but it will also allow for longevity of the existing light systems. Safety is also something that we keep in mind when developing this prototype. Something that's actually really helpful is that digital electricity is very safe. You can actually touch it and nothing would happen to you. So just working with these systems, they're very efficient, they're very safe. So this also allows us to have a safe prototype and maximize safety out in the field. Over the past year, we worked to successfully deliver a light sensing device which can interface with VoltServer's ETX8 to control the brightness on artificial grow lights to maintain an optimal level of light. Some of the key features to achieve our ABO, or anticipated best outcome, are the testing of the light sensors. There were some test boards that were developed, and these test boards were used to determine if the light sensor was good or not, depending on what we needed to do. We tested 3 different types of sensors, and from there we chose the best one and we moved forward to the next stages with the best performing sensor. There was also a sensor layout that needed to be figured out, and this was due to the loss of reading data based on the angle of the light. This was figured out because in the datasheet of the sensor that we used, it shows that based on the angle that the light's hitting the sensor, we received different data readings. Also, we needed to create an IP-rated casing. This allows the sensor to exist in an environment where water or dust is not gonna get in the way, and we're not gonna have any problems putting it out in the field. And finally, also we needed to develop the software and the GUI so the user can set a different threshold if they wanted to, based on the light they want the plants to be at. And this was done using Raspberry Pi. One of the first key accomplishments of the previous semester was the testing of the light sensors. So we did our research and we determined that the 3 sensors presented right now were the ones that we would choose to test. One of them being the LTR329 ALS from Light On Technology. The reason why we chose the sensor is because it had a really good reading resolution. But one of the challenges was that the packaging was a bit complicated to solder and to test because the pads were underneath the sensor. Because of this, we looked at different alternatives, one of them being the BH1730 FBI from Rome Semiconductor. Other than being easy to solder because we didn't have to worry about the pads being underneath, it also had a really good detection range, which was 0 to 100k lux. But the sensor that we ended up going with at the end of the testing stage was the BH1750 FBI. Basically had the same benefits as the BH1730 FBI, but the main advantage was that this sensor allowed us to have two different I2C addresses that we can toggle between low or high.
Another key accomplishment was our sensor array design. This was created in order to reduce the angle of light incident on each sensor. There is a loss depending upon the angle of light incident on the sensor that you can see in that graph on the right. So we wanted to try to reduce this to be as low as possible. While the design does work, we were unable to use this due to unforeseen complications with I2C communication. However, with small edits to our PCB design, we would be able to still utilize this. So the theory is still there. Another key accomplishment is with our casing. Our casing consists of a 3D printed bottom, a 3D printed interior, and acrylic box for the top. The acrylic box on the top is needed because we need to allow light to get into the system in order to hit our sensors with minimal loss, while also protecting our system from the elements such as water. Inside the 3D printed exterior is a 3D printed mount for the Raspberry Pi to be screwed into, and this will house our system. Continuing with our casing, you can see this is our final product inside our CAD software. You can see that there is the acrylic box covering up a 3D printed bottom and a 3D printed interior. Each of those face-looking things is where one of our PCBs would be mounted to, and the PCB mount is inside. Also, what you can see is a hole in the bottom of the black casing. This would be for our power supply, which supplies 5-volt DC power to the Raspberry Pi, while also creating a watertight seal due to the IP-rated connectors that we used for the system.
One of the key accomplishments we had on the team this past year was developing the software package for the project. The basis of this software project is a Python script that runs on the Raspberry Pi. This handles the readings from the light sensor over I2C and also outputs the commands to the lighting units on the VoltServer ETX8. It also communicates with the MySQL database, which acts as the middleman between the Python code and the graphical user interface. The graphical user interface was developed using HTML, CSS, and PHP. This takes in inputs from the user through a web page that they can access from their browser and returns the values to the MySQL database so that the Python script can read it and then manipulate the data and control the lights with that data.
Hello everybody, my name is Rowan Woods, and I'm here to talk about the economic impact for VoltServer using our AgMesh Capstone. So our project has a low cost reduction for each individual sensor, construction, and total package cost. Our project has a low energy consumption for the consumer by only using the light when it is needed for the plants versus being on constantly. This in turn lowers energy consumption while still ensuring proper plant growth regardless of the conditions. Up next, I will discuss my individual technical contributions towards our AgMesh Capstone project. Some of my early accomplishments include hardware component identification and research, where we identified the BH1750FVI light sensor as our best hardware component to use for our project. This included reasons such as I2C addressing, cost, and also ease of use and implementation. Additionally, I tested our test PCBs and soldered them, as well as contribute towards our sensor array design and took preliminary measurements and data acquisition from our local URI greenhouse 107. I largely contributed to the construction of our PCBs and hardware components. Some of the lessons we learned from this were the trial and error on our construction techniques, where we found that the best avenue for our construction for our cables and soldered PCBs was using soldered single solid cable glands versus threaded connector pins on our connection boards. Additionally, testing individual parts before joint construction will lead to a more simplified testing process where we can identify problems faster, as well as also ensuring that our PCB design schematic is correct, which will save us additional time and effort, problem solving and troubleshooting. Additionally, I worked on our early CAD modeling as well as our prototype construction this semester. Early in the semester, I began work on our new CAD design model with a 17-face dome, which used optimized angles for increased efficiency and accuracy on our light sensor array. In addition to this, the construction of our physical prototype with all embedded cables, electronics, hardware, and other components was assembled towards at the end of their semester and was tested to make sure that all components used would work and gave proper readings. Some lessons we learned from this was that CAD is quite a difficult program to learn, especially if you're new to it, which is why I was handed over to Zach Chauffet, as he just showed more proficiency with the program, as well as also making sure that all of our physical products are the right shape and size for our construction and also in our design process.
Hi, I'm Andre Costa, and I'll be going over my personal accomplishments from the past year. My accomplishments from the first semester were designing the test PCBs, along with the initial assembly and soldering of some of those first test PCBs. I also worked on the development of the code for reading two ROM BH1750 FVI sensors over I2C. I also created a localhost MySQL database on the Raspberry Pi and wrote a Python script that can send data to the MySQL database on the Raspberry Pi. Along with that, I also got the initial setup for the Apache web server running on the Raspberry Pi. My personal accomplishments for this project over the last year was the development of the full software package. This included a web interface which used HTML and CSS with embedded PHP to allow for communications to the MySQL database from a web browser. This also included the Python software package, which was in charge of collecting the sensor data and updating the MySQL database, making adjustments to the light level based on the environmental readings, and utilizing a bash script in order to change the brightness on the artificial grow lights connected to the ETX8. The key lessons I learned this semester were how to develop a web page with embedded PHP to allow for functionality between a web page and a MySQL database, and also how to execute a bash script from within a Python script. I would now like to introduce Edgar Ponce so he can go over his technical accomplishments from the past year.
Thank you, Andre. Some of my early accomplishments from the fall semester were the contribution to sensor research. This included looking at the pros and cons, making sure that the sensors that were being tested properly, and also that we look at all the benefits and the disadvantages of all the sensors in comparison to other sensors. This was a very crucial step to making sure that we start the project the right way, and this took a lot of time and a lot of effort from the team as a whole. I also contributed to the software to be able to test these sensors. We mainly tested the sensors using an Arduino Uno, which was easier and it was faster than programming a Raspberry Pi. It was also more accessible since we didn't have a Raspberry Pi at the time. I also worked on some PCB designs. I started the very early development of the PCB designs that were going to be used later on in the semester or in the spring semester. I also developed a testing PCB for the BH1750 FVI using Arduino Nano Every, and this way we were able to validate the performance of the sensor. And also I had to learn and I had to do research on I2C communication protocol, just because this is the way that our sensors were communicating with our controllers. Going more into detail about PCB development, I designed two PCBs, one of them being the sensor PCB and also the connector PCB. The sensor PCB allows us to sense the ambient light and return a lux value to the controller. This was thanks to the BH1750 FEI sensor. The connector PCB was used as a Raspberry Pi hat, and it allows us to turn power on and off to all the sensor boards so we can read one at a time. Some of the lessons learned were that we must build a breadboard to verify the operation of PCBs before taking the time to design a whole PCB and ordering it without first making sure that our concept works. And also another thing that I learned was that we need to really pay attention to the data sheet as well as the design of the PCB. Constant cross-referencing is really good to make sure our PCBs are solid. I also contributed to PCB building. This took a lot of time and effort, mainly because the PCBs were very small, and a lot of attention to detail was necessary in order to make sure that these sensors and all these connectors were soldered correctly. Some of the lessons learned is that we need to test the boards as soon as possible to anticipate any issues. As soon as the boards arrived, the boards need to be built and need to be tested, and we shouldn't wait until the last minute to test the boards just in case there's anything wrong with it. Another good thing that I learned is that we must also test all boards for solder, make sure the solder is properly applied, and that there's no shorts or anything of that sort. Another contribution of mine was code development. I worked with the sophomore David Quevedo, who joined the team on Replit, which allows for live collaboration, and we worked on developing a code that controls the GPIO pins on the Raspberry Pi for the connector board, so we can turn power on and off to the sensor PCBs, so we can read them one at a time. Also, we made sure that all the I2C communication was included in the code and that it worked. This was also done by Andre, which was a huge help, and we were able to work together thanks to Replit, and that was another one of my contributions. Now I would like to introduce Zach Jofe so he can tell us a little more about his contributions to the project.
Early on, my individual contributions included designing the sensor array design that I talked about earlier. Additionally, I looked into a PAR sensor. What a PAR sensor is, it is specifically designed for reading the wavelengths of light that a plant needed. However, we decided that we did not need this, as it would be a significant cost increase while not contributing much more of needed information to the system. We just needed to know that the light was at a certain level, which we have with the sensors that we chose. Later in the year, my biggest two tasks were the CAD design and housing creation, as well as the power supply creation. The CAD creation had to go through numerous different iterations, as well as numerous different edits to support the printing. The power supply had to take in a 120 volt AC and convert it down to a 5 volt DC, while also being able to be weatherproof with our IP connectors. A few lessons that I learned were to test everything. There were a couple things such as with our PCBs that I did not think we would need to test. However, it turned out that they provided faults for our system, and therefore we could not use some of our designs. So that was one of my biggest lessons. Another lesson that I learned is just 3D printing. I'd never 3D printed before. I had never used a CAD design before. So that was a big lesson that I learned, was how to do that and some of the complications that can arise from 3D printing. In summary, our ABO was achieved. We developed a prototype that is able to change the brightness of the LEDs in the agricultural house in order to satisfy the brightness that each plant needs. An alternative solution that we had to the prototype that we created is to actually use the sensor array design that we designed. We weren't able to do this because there were complications with I2C. You can't have numerous sensors off on an I2C bus, or else it messes with the communication. We figured this out much too late in the process, and we weren't able to design other PCBs to fix this. However, it is a very simple fix because the sensors that we used have different addresses. So if we were able to toggle the address instead of turn off a device, it would be a different solution to the problems that we have, and it would be able to have numerous different sensors eliminating the angle loss that we communicated about earlier. We would now like to thank our two technical directors, Camilo and Stan, as well as Dr. Sunak, for their support and leadership throughout our capstone project. We would also like to thank Dr. Zhong for allowing us to use his power electronics lab.